Let's talk about beams and bending for real this time. So anytime we have a beam, which again is just something that is loaded perpendicularly to its longitudinal axis, right? So beam, some long member like that undergoes loading. And what happens in real life, what that looks like, is that when you subject it to loading, you get this curving happening, right? If I have this straight beam and then I load it, you can see that there's some deformation there that happens in this curving kind of way. So it curves in this sense of horizontal, right? Our horizontal lines kind of curve, and then our vertical lines mostly remain straight. So if we were to draw this out, what it kind of looks like is happening, like a super exaggerated form like that. The beam is curving right into like a C shape almost, where it's almost forming like this circle. You could like bring all these points together if I could draw like a little bit straighter. Where it's kind of coming into this central point. This point here we call the center of curvature, right? It gets this curve in it. Curve. Okay, pretend I can spell. Curvature. The center of curvature here. So what's happening for every little slice dx here, there's this angle that it's moving through, but more importantly, we're getting this top line here. The top of our beam is shortening, right? The top shortens and goes through compression. Top shortens. It gets compressed. Whereas the bottom here is actually lengthening. So this is getting elongated. The bottom gets elongated and is held in tension. So if we were to look at any one given of these dx slices of some beam here that's being curved, that's being bent, going through deflection, we were to look at a little slice dx, and we looked at what was happening with this compression and tension, what we would see is we have this relationship for strain going on, right? Where we have this strain that is being compressed, right? It's being pushed in the top here, little by little, until we hit the neutral axis, which happens at your centroid. The neutral axis, your centroid of your beam. And then we start to see the strain get a little more and a little more and a little more in tension. So our strain, we're in compression, we're losing this little bit of length here at the top. And then as we go out, we see that we're gaining a lot more length here at the bottom than we did along the neutral axis. The neutral axis, this stays the same length here in the center. So there's no change there, but we have this strain relationship where at the outermost edges we're experiencing the most strain, which of course we can relate strain to stress, especially if we're working in our linear elastic region, which we're going to assume that we are. So this is also going to be where our maximum stress is occurring. It's going to be occurring right on these outside edges. Just one side is going to be in tension and one side is going to be in compression. So as we're looking at this, we're going to make a few assumptions before I give you this equation that we're going to use for this stress, this bending stress. This is going to be our bending stress that we're discussing. We use the same as normal stress, this sigma here. But a few assumptions that we're going to make as we're talking about this. We're going to assume we're in the linear elastic region. we're going to assume our cross-sectional area is symmetrical about some axis. This is just going to save us a lot of integrating and calculations. So like a square cross-section is symmetrical about two axes, or one that we see a lot, like an I-beam, an I-shaped one, also symmetrical about both axes. It doesn't have to be. It could just be, maybe like a C shape, symmetrical about a single axis. That's fine. We're just going to assume the cross-section is symmetrical about the neutral axis. We're also going to assume it's a single material for now. Composite beams are going to be a special case we'll look briefly at. But for most of these problems, we're just going to assume it's made of one single material. And then finally, we're going to assume that the length does not change. So this neutral axis length here, we're assuming that this length does not change. Even though on the outside, this is in compression, this is in tension, these outer lengths may change, the neutral longitudinal axis does not change in length. And we're going to ignore the lateral strains from Poisson's ratio. So even though we're seeing strains in this direction, we're going to ignore them in the other direction for now, just as we get used to beams and bending and how we calculate these things. So in order to calculate our stress in a beam that's bending, right, our bending deformation, we use something called the Flexure Formula. And I'm gonna spare you the derivation details. But the derivation is extremely similar to what we saw in torsion. So our bending stress equation is going to be a moment times C, this is for max, moment times C over moment of inertia. Or at any given point, it is the moment, the bending moment, times y over the moment of inertia. And let's break those down a little bit. So anytime we're undergoing this bending, what we're assuming happening is a moment is being applied, right? So a moment is just a force times a distance. So it could be some force that is causing this beam to move down, but we can just multiply that force times a distance. That's what's giving us this moment. It's really an applied moment at a cross-section of interest, right? So we would take a chunk out of here, or make, section AA, take a chunk out of there, figure out what the moment is, which we can derive from our shear and moment equations, shear and moment diagrams. It could be given to us. There's a lot of different ways we can find the moment, right? Even just throwing back to statics and doing an equilibrium to find a moment at the internal section. Any of that works to find a moment. So this is the moment. Your C here is your distance from the neutral axis to the outer edge. So you might notice this is really, really similar to the torsion equation. Right, we said our shear stress was torque C over polar moment of inertia. Now instead of torque, we're using a moment, and instead of the polar moment of inertia, we're using the regular moment of inertia. So it comes from a similar idea here, where this C is that outermost value that we were looking at in torsion. This C is going to be that outermost value away from the centroid. So if we look at, say, this guy, for example, that C value, right, is going to come off the neutral axis there. This distance is going to be C, right, this distance here. So it is the distance from neutral axis, typically your centroid, to point of interest. And so that's why we have it in both forms here, because your point of interest may not always be on the outer surface. We use this C value if it is all the way on the outer surface, like the maximum, but it doesn't have to be. You could want any given Y value away from that central axis. So your Y value being just some arbitrary distance away from your centroid. And then finally, I is your moment of inertia. So this is again going to be another throwback to statics. We remember at the very end of statics, we had a few equations for moment of inertia. We had, our moment of inertia is the integral of y squared dA. Again, in this class, we're not going to work with it in integral form really. What you're going to see more often is if you have those distinct shapes, like a square, those have their own moments of inertia, right? A square is base height cubed over 12. There may be times where we need to use parallel axis theorem too. So that's your moment of inertia plus AD squared. And I won't go too in depth through moment of inertia. We recapped this at the very beginning of class, but this is when we will apply these moment of inertia ideas. It's in this bending stress. This bending stress. We're going to use moment times the distance from the neutral axis divided by that moment of inertia. So this is when this all comes back to help us do these calculations, right? It's just a property of the geometry that helps us figure out what the bending stress is in a beam. So let's go ahead and take a look at some examples that will help make this make a little more sense. So to start out with just a super straightforward example, we want to find the maximum stress in this beam. And we're given this little cross section here of 30 millimeters by 60 millimeters, and they give us what the moment is in the beam right here. The moment at this section is 40 Newton meters. So all we're going to do is we're going to grab our bending stress equation, moment times C over moment of inertia. So all I need to do is pick out each one of those. Sometimes you're going to find that every single one of these components is going to require a calculation. Other times things are just going to be given to you. So in this case, my moment is 40 Newton meters. Boom, given to me, 40, already done with that. Next one is C, and that's the distance from our centroid to the outermost portion here. So our centroid for a rectangle is going to cut just halfway through, right? It's going to cut right through the center there. So this means that my C value going to be this distance halfway here. My C value is going to be 15 millimeters, right? Cuts halfway through that 30 millimeter height there. This is the distance that I'm looking at, so 0.015 meters. And then finally, I need my moment of inertia, which for a rectangle, again, we can look up in the back of our book or in our class formula sheet. We have some of those have some of those standard shape moments of inertia. So for a rectangle, the standard shape one is base height cubed over 12. So in our case, that's going to be 0.06 times 0.03 cubed over 12. And that's going to pop us out an answer. And now we can plug all of that stuff into our into our normal stress equation. So the moment was 40 Newton meters times 0.015 meters all over. When I punch that moment of inertia into my calculator, I get 1.35 10 to the negative 7. So this gives me a maximum stress of 4.44 megapascals. 4.44 megapascals. So it's pretty much plug and chug. You just have to know where to find each of these three pieces of information. So this is typically the way I tackle these problems, is I go, all right, what's the moment? Do I need to do anything to find that moment? I move on to C. Do I need to find a centroid? Do I need to do anything to find C? Let's find what the C value is, and then the moment of inertia. Mostly because moment of inertia is a huge pain in the butt sometimes. So I like to save that one for last. And then I dump all of those three ingredients into my recipe, and I mix them together in my equation, and I get my answer, right? Plug and chug. So this was a pretty simple example, but let's look at something a little bit more complex. In this example, we have a chair supported by this fixed arm A. So the chair is not sitting on the floor, it's totally supported by being fixed to the wall through this arm. And we want to know if a 180-pound person sits on the chair, what's the max stress in section AA? So we want to look at just this cut through section at AA, figure out what the max stress is just right there from this guy sitting on the chair. And they give us the cross section here too, which is a rectangular cross section with a rectangular hole in the middle. And it looks like their centers overlap. So they're going to have the same center, which is going to save us a little bit of calculation because they're going to have the same centroid. We don't really need to calculate a centroid for this. But this is going to be our cross section. It may be a little more complicated since it's hollow. But what we're going to do first is we're going to just write down our equation. Moment times distance away over moment of inertia. So we're going to go through and find all of our ingredients for this, right? Now our moment, we'll notice we're not given a moment outright. We're going to have to find one. And again, we want to know what's happening at section AA. So if I were to draw myself a little free body diagram here, I have my 180-pound person who is 8 inches away. Here's the cut, right? Here's section AA. If I look at section AA, I have my internal moment in there, right? I would have my internal moment, my shear, my normal force. All of those internal forces would be bleeding out if I cut through this section AA. So this is how I go about finding my moment, right? I can set this up as an equilibrium, or I can just say, you know what, a moment is a force times a distance. The moment is just going to be 180 times 8. Right, so some of my moments, it's going to be moment plus 180 times 8 inches. So that's going to give me a moment. I drew this the wrong way. It's actually a counterclockwise moment. Sorry, a clockwise moment. Moment is going to be 1,440 pound inches, right? 180 pounds times 8 inches gives me pound inches. So again, not too bad. Just some basic statics to find that moment that we needed. Now we need to find that C value, right? And that's going to be just our distance for our max stress. It's going to be our distance from the centroid to the outermost edge. So our centroid in the middle here to the outermost edge is going to happen halfway between this. So half of 3 inches means that our Y value will be 1.5 inches. Right, that takes it all the way to the outer edge from our neutral y-axis. And then finally, we need our moment of inertia, which for a rectangle, we can again use BH cubed over 12. Now the key with this guy is he does have that void in the middle, right? He does have that hole through him. So luckily, since their centroids line up, to calculate this, all we have to do is a subtraction. BH cubed over 12 minus the void, BH cubed over 12, which in this case is going to be the base is 1 inch, the height is 3 inches cubed over 12 minus my void base is 0.5 times the void height is 2.5 cubed over 12. And I can punch that into my calculator to get 1.6 inches to the fourth, right? These were all in inches. Moment of inertia always gives me a length to the fourth power. So that gives me everything now, and I can plug all that in. So we can say 1440 pound inches times 1.5 inches divided by 1.6 inches to the fourth is going to give me around 1350 psi. 1350 pounds per square inch, or 1.35 ksi if you like that better. You can do any conversion you like with this one. Again, I think staying in inches for something like this is a little bit simpler than trying to convert everything into feet and then getting lots and lots of decimal places. But it's up to you. You could have converted everything into feet and gotten some pounds per square foot type of stress here. It's all about how you calculate it. Let's take a look at another example. So here we've got something a little bit more complicated. We want to find the max stress in the beam still, but now we have this simply supported beam that has a distributed load on it, and we have a cross-section that's an I-beam, right? It's not a nice rectangle that we can just use our little BH cubed over 12 formula on. So we're going to have to do some extra steps with this one. So again, we always start out, let's see what we need. MC over I. I'm going to start with my moment. Now, my moment here, not given to me, and I need to find my maximum moment to find my maximum stress, which means I need a shear and moment diagram. Right? That's the only way I'm going to be able to find what the maximum moment here is. So luckily my reactions are pretty straightforward. Since this is a totally symmetrical beam with a distributed load only on it, I know that each side is going to take on exactly an equal amount of that load. So this is 5 kilonewton meters over 6 meters. That's 30 kilonewtons. So each side is going to take on 15 kilonewtons. And now my shear and moment diagram will be pretty straightforward because I only have the single load region here. So it looks like for my shear diagram, I pop up by 15. I pop up by 15, and then I go down by 5 kilonewtons per meter. I go down 5 kilonewtons per meter until I hit negative 15, because this 15 is going to pop me back up to 0. All right, so 0, go to 15, come all the way down with a slope of negative 5, down to the negative 15. And then that reaction of 15 kilonewtons pops it back up to 0. Pretty straightforward. That's my shear diagram. But more importantly, I got to build my moment diagram. So now I already know where the maximum is going to occur now. It's going to occur where this shear diagram crossed the x-axis, where it crossed 0. Right, so I can go ahead and draw in this moment diagram, right? I know what it looks like. It's gonna be a parabola, kind of a crummy parabola. Let's try again. All right, that's a little bit better. It starts in 0 and ends at 0. And really, I just need to find that maximum. So I could go ahead and like cut through the beam here and do a whole calculation. Or I could know that this maximum is going to be the value of the area under this curve. Right, area under the curve is going to give me this max moment right here. The area under this curve is 1/2, since it's a triangle, 1/2 base times height, 1/2 15 times, this occurs exactly halfway through the beam, so 3. And that's going to give me a moment of 22.5. Now we could have also just split it here halfway if we had known that this is where the maximum moment was going to be before drawing these diagrams. You could just make this cut here and calculate the moment, but this is what the maximum moment is, and it occurs halfway through the beam. And this units is kilonewton meters. So that takes care of our moment. Now our C value, again, is just the distance from the centroid to the outermost axis. So in this case, it's 150 plus 20. So 170 millimeters. 0.17 meters. And the last thing I need is that moment of inertia. Moment of inertia. And I don't have a really good way to calculate this other than using my parallel axis theorem. Right? So my parallel axis theorem, if you remember, I divide this up into shapes and I calculate the moment of inertia for each shape. And then I use that parallel axis theorem, that a times d squared, to offset it, and I sum everything together for each individual part. So for me, I like to use the table version when I'm calculating this. I'm going to move this down for reference, but I like to use a table. So for me, I'm gonna call this wide part shape 1, and like the skinny inner part, I'm gonna call that shape 2. Right, so there are 2 shape 1s here. There's 2 of these upper flanges, upper and lower rectangle, and then there's 1 center rectangle. So when I go to set up my table, what I do is I like to write in what the shape is for my moment of inertia parallel axis theorem, sum of the moments of inertia plus AD squared. I like to do the shape. So my shape, I'm going to have, I'm going to call it flange 1, and then the top and bottom are the same, so these two are going to be essentially just doubling each other, right? There's a top bar and a bottom bar. And then there's the center. I like to take these, I like to put in my moment of inertia calculation, which, since these are all rectangles, they're all going to use base height cubed over 12. But if they were different shapes, then they would use the specific shape ones that they needed to. Then I'll do an area calculation. Then I'll do D is distance away from the centroid. And then AD squared. So that way I can sum this first column and the last column, and that's going to give me my answer for moment of inertia. So for the first flange here, my base times height cubed over 12. My base is 250 millimeters. So 0.25 times height is 20 millimeters cubed, or 0.02 over 12. And that gives me a value of 1.67 times 10 to the negative 7th. So again, that's for both flanges. I've got a top and a bottom. I'm going to put that in for both of them. And then for my center line here, it's going to be a base of 20, 0.02, times the height is, it's 150 each direction, so that's a total of 300. 300 millimeters, or 0.3 meters, cubed over 12, which gives me the base moment of inertia 4.5 times 10 to the negative 5th. I've got my base moments of inertia, and calculate my areas really easily, right? Just base times height. So for each of my flanges, 250 times 20, which converted to meters, 0.005. Same for top and bottom. And then my center line here is 300 millimeters times 20 millimeters, 0.006 meters squared. Then I'll take this distance. This distance is the distance of the centroid of each shape minus the centroid itself. So for example, section 2, my center shape shares the same centroid with the overall shape. And since they share the same centroid, this would be 0. There is no distance between the centroid of the shape and the centroid of the overall shape of the mini shape versus the overall shape. But for our flanges, they do have a different centroid. Right? Their centroid occurs halfway through this beam, right? 10 millimeters into this beam. So that distance away is that 150 millimeters plus that 10. So their centers are 160 millimeters away from the center. 0.16. 160 millimeters away from the center. And then for this last bit, I just plug into the calculator d squared times a. So d squared times a is 1.28 times 10 to the negative 4th. For both of these, and then of course times 0 is going to be 0. So the very last thing is to just sum everything down the columns here. I need just like a little bit more room. Move this up. Need just a little bit more room to sum everything down the columns. So I sum everything down this column, my I, and then I sum everything down my final column, and I add those values together. So it gives you 2 times 1.67 times 10 to the negative 7th, plus 2 times 1.28 times 10 to the negative 4th, plus 4.5 times 10 to the negative 5th to get your I value, your moment of inertia, which is going to be 3.01 times 10 to the negative 4th meters to the 4th. Whew, that was a lot of work to get that moment of inertia. But once we got there, now we just have to plug everything in, right? So this is our I value. So final step here, stress is 22, I'm going to convert this 22 kilonewtons per meter to be 22,500 Newton meters times C, 0.17 over that moment of inertia we just found, 3.01 times 10 to the negative fourth. Punch all that into my calculator and get a bending stress, a maximum stress of 12.7 megapascals. 12.7 megapascals, or 12 times 10 to the 6th pascals. Any way you write that answer is acceptable, but that is our max bending stress in this beam. And this value is really important, right? This value is what's going to help us pick things like what kind of material we can make the beam out of, right? If it can't withstand this maximum of 12.7 megapascals, then we can't use that material. So we use all of this information, we do all of these calculations for design, right? They help us pick out exactly the criteria we need to meet when we're designing something. I've got one more kind of bonus example here, just to show some of the nuances and calculations and some of the tips and tricks that we can use when we're approaching these problems. So here we have another beam, of course. We want to find the max stress, but it's got a couple of odd things going on. So one, it has this like diagonal lacing kind of running through it, and the problem tells us to ignore that. We're going to ignore that diagonal lacing. But more importantly, we're going to look at this cross section. So the lacing kind of represents this little line connecting these two circles. But really the cross section is a tube, a large tube stacked over a smaller solid rod. That's what makes this quote unquote beam. It's a tube over a rod. There is some lacing connecting it. We're gonna say that it's negligible for this problem. It's so small, it's not really going to have an effect. So we're really just looking at big tube over small rod. And we're given this setup here where we have a beam that is supported on both sides, and it has a distributed load in the center. So again, we're going to go ahead and do our whole setup, finding that stress is moment times c over moment of inertia. So luckily from the last problem, we know that when we have something that is completely symmetrical like this, that our reactions on both ends are going to be the same. So for this, I can simplify the distributed load to be 600 pounds, right? 6 times 100, which means that each of these reactions is going to be 300 pounds. Each of those two end supports. But we also know from the last problem, when we have something that's totally symmetrical like this, that our maximum moment is going to occur right in the center. So we don't actually have to go through that whole thing of drawing a shear and moment diagram to find what the max moment is. We can actually just say, all right, I know it's going to be right in the center. If I draw this free body diagram, this is 300, then we hit the distributed load, right? And we only hit halfway. So we've got the 6 feet, and then this is 3 feet, 100 pounds per foot. Our max moment is going to occur right in the center of the beam here. So I can go ahead and calculate my moment off of this free body diagram that I've drawn. So here, I've got my moment is going to be moment minus 300 times 9 plus 100 times 3 times the resultant distance away, 1.5. But I can use this to find my moment value, 2250 pound-feet. Actually, I'm going to go ahead and put this up here so I can keep track of everything. 2250 pound-feet. Again, you can go through the shear and moment diagram if you want to, but since we know where this moment's going to occur, I just went ahead and calculated it using my static equilibrium, cutting through there, finding that internal force. So luckily the moment on this guy wasn't too bad. But we come to this C value. And normally our C value is pretty straightforward. It's just the distance from the centroid to the outer edge. But in this case, we have this tube and this rod. We're not given where the centroid is. We're going to have to find where that centroid is. So you may recall from way back at the beginning, we talked about how we find centroids. We talked about how we find moment of inertia and centroids at the same time. Talked about it in statics too. But that centroid equation is just the summation of your centroid for each shape times the area over the summation of all of your areas. So in our case, what we have is this tube circle and then this rod, this solid circle. So for the tube, I'm going to give myself a reference axis. I'm going to say I'm measuring everything from the bottom here. And then my centroid is relative to this bottom. So this is my reference axis. You can pick your own reference axis, but I would make it something that's easy to follow. Right, so using the very bottom as a reference axis is pretty helpful. So I'm finding my centroid of each of these shapes relative to that centroid axis. So for my bottom rod here, my centroid is going to hit halfway through the circle, 0.25 inches. And then times the area of that circle, which is pi over 4d squared. So pi over 4 times 0.5 squared. That's my first YA term. Then I can do the same for my tube up here. So plus the distance to the center of this. Center happens right here, 0.5 inches up. That's 0.5 plus 5.75 plus 0.5 is 6.75. That's the location of this centroid here. 6.75 times pi over 4 times, I have to subtract the diameters, right? So d outer squared minus d inner squared for that tube. So the outer diameter is 1, but the inner diameter here, my thickness is given to me as 3/16 of an inch, which means that this distance here is 3/16 and this distance here is 3/16. So my outer diameter here is actually 1 minus 3/16 minus 3/16. So that diameter, that gives me, what is that? 6/16. 6/16 is 3/8. 1 minus 3/8 is 5/8. 5/8 squared. And then I divide all of that by my overall area. My overall area is added together. So the 0.05 squared plus the 1 squared minus the 5/8 squared. And they're all multiplied by pi over 4, so I just move that term out to the side here, but you can keep them all together if you like. And I punch all of that into the calculator just to get this centroid value of 4.86 inches. So that tells me that my centroid is hitting somewhere in here. Somewhere in the center through that ribbing. This is where my centroid is hitting. Now I just have to figure out my C value. So it can be in either direction, right? My C value can be either from the centroid to the bottom edge. This could be my C, or it could be to the top edge. All of the cases we've seen so far have been symmetrical, so we haven't had to pick a C value, but we want to go to the farthest axis out, right? Farthest away point from the centroid. So out to the bottom, this value is 4.86. And out to the top, it would be this full length here is 7.25. So it'd be 7.25 minus 4.86 would give us this value of 2.39 inches to the top. So obviously this 4.6 value is larger. So this 4.6 value is actually going to be our C. That's the distance from our centroid here to this outer edge. It just happens to be the same as our reference axis centroid here. So we've got our C. We've got our moment. Now it's just that moment of inertia. That moment of inertia, once again, coming up parallel axis theorem style, right? So much like in our last example where we were taking a shape and breaking it down into rectangles and using parallel axis theorem to calculate the moment of inertia, we're going to do the same thing here, except this time our shapes are all circles. So we're going to have our little table. I always like to do it table style. So I've got my shape, the moment of inertia for the shape, the area, d, and then AD squared. So my shape, I have 3 shapes going on in this guy. I have solid circle, upper solid circle, and upper void circle. So I'm going to call this top circle, and then negative top circle. So like the void portion, the portion that gets subtracted out. And then bottom circle. I guess I could call this top void as well. But void just indicating that it's going to be a negative. Everything there is going to be subtracted out. So for circles, our moment of inertia, if we look it up in our charts, in our tables, or if we remember from our torsion section, for a circle, it's pi over 4 r to the 4th. That's all it is, right? For this basic moment of inertia. So for our top circle, it's pi over 4. And remember, this is radius to the 4th. The diameter is 1 inch, meaning our radius, 0.5 to the 4th. Punch that in my calculator, I get 0.049. And then I just go down the line and repeat, rinse and repeat. Now this guy have pi over 4, that inner diameter we said was 5/8. So half of 5/8 is 5/16 for the radius. 5/16 to the 4th. Now remember, this is a void, so this moment of inertia is going to be negative. So here I get a negative 0.0075. Very important that that goes negative into your summation. And then finally that bottom circle. It had a diameter of 0.5 inches. That's a radius of 0.25. Punch that in my calculator. 0.0031. And then I'm just going to keep on working down the line, right? Area of a circle is pi r squared. Pi r squared. We already got all of our r's over here. So pi times 0.5 squared gives me 0.785. Same deal for the next one. Pi times 5/16 squared gives me 0.307. Again, this area is going to be negative because this is a void, right? The center here is a void. Not there, gets negative, subtracted out. And finally, my bottom circle is pi times 0.25 squared, 0.196. Ooh, okay, now we just have our D column, which D again is the centroid of the shape minus the overall centroid. So the overall centroid is 4.86, and the centroid for our upper guy here occurs at 6.75. So this is going to be 6.75 minus the centroid value of 4.86. It's going to give us 1.89. The top circle and the negative both have the same centroids, so this is the only thing that doesn't get a negative put on it. And even if you put a negative on this D, this term gets squared anyways, so it doesn't really matter if it's positive or negative. It's going to end up as a positive. Then it's multiplied by the negative to make sure that it's negative, right? Okay, and the last one is going to be 4.86 minus 0.25 for that bottom circle, right? The centroid of this bottom circle happens right here, 0.25. And the difference between that 4.86 and 0.25 is 4.61. The very last thing, just finish out this column here so I can do the summation of AD squared. So 1.89 squared times 0.785 gives me 2.81. Work it on down the line. 1.89 squared times negative 0.307 gives me negative 1.1. And then my 4.61 squared times 0.196 is 4.17. So now I just add everybody up. Right, take a summation here. So I sum down my moment of inertia column, 0.0447. Sum down my AD column, 5.88. And that gives me a total moment of inertia, when I add these two together, of 5.927 inches to the fourth. And that was the very last thing that I needed in order to come up and solve this equation, which I've kind of run out of room to actually do here now. But that's okay, that's okay. We will just, we don't need this centroid calculation anymore, I guess. He goes away. So our max stress is going to be, let's see, 2250 pound-feet. Ooh, I think all my other things were in inches, right? Yeah, everybody else is in inches, so I'm going to include a conversion in here. I can get that into inches. 12 inches per foot. That per foot will cancel out with the foot. And then I'm going to multiply by my C. That's in inches, and my moment of inertia is in inches. 5.927 inches to the fourth. Put all of that into my calculator, and I get 22,000 ESI, or 22.1 KSI as my max stress in there. So there are a lot of different little pieces of statics, a lot of different little pieces of geometry and calculus, the shear and moment diagrams, moment of inertia, centroids, all of this coming together to make these beam problems a real problem in your life. Right, so lots of little things, little details to keep in mind when you're approaching these beam problems. They seem really simple on their surface, so there's only 3 components that you need to calculate this stress, but finding each of those components is what's really important. Those are the steps that you really got to get down, is finding all of those components so that you can get the correct stress.